Okay, so this problem here is an AP exam free response number 1 question. The last part of this question needs to have the graphing calculator for this. Oh, it looks like this is something's gone wrong with my notation here. Okay, I think that's W prime right there. Okay. So part 1 says use data to estimate W prime at 12. Okay, so notice that there we have the W function. This is a water, I think the water temperature, and then the minutes. We want the change of the water temperature at 12 minutes, which is in here. Now this is a specific AP problem where they want you to estimate the slope, okay, between these 2 points. Okay, so 12 is going to be in there, so we're going to estimate the slope in there. So we're going to find the average slope from 9 to 15. So we're going to say that W prime of 12 is approximately equal to the rise, in this case, is 67.9 minus 61.8 over the run of 15 minus 9. And that's going to give us an estimate of the slope at that point. So we're going to get, that's going to be 6.1 over 6. Okay, so as a decimal value, that's 6.1 divided by 6, about approximately 1.01, 1.02 degrees. I think this is Fahrenheit per minute. Okay, so that is how we would find estimates of slopes when we don't actually have a coordinate there. So we're going to use the data there as well to analyze the integral of this, which is the area under that curve. Okay, so we're going to use a left-hand Riemann sum for this. Does it say? Yeah, it says asks us to analyze this. Okay, so this is finding the integral underneath the derivative, which is essentially using the fundamental theorem of calculus. If I want to find the integral of this derivative, W prime t, we're really finding the displacement from 0 to 20. Okay, so this is going to be 0 to 20 of W prime of t dt. Okay, that's going to be big W of t and the displacement from 0 to 20. In this case here, we're going to end up with, we can just go back to this then represents the antiderivative of that function. It's going to be 71 degrees Fahrenheit minus 55 degrees Fahrenheit. Okay, so we get a net change of 16 degrees Fahrenheit. Okay, so make sure that we analyze the units. So that W prime represents degrees Fahrenheit per minute. The integral will represent the degrees Fahrenheit, or the net change of degrees Fahrenheit. Okay, so part C is the average value. Okay, so we're going to use the average value of not the W prime, but the W function. So we're going to take the area under this curve and then divide it by 20, because that's the interval width is 20. Okay, so it looks like this. So 1 over 20, the area underneath the curve of W using a left-hand Riemann sum. Okay, so left-hand Riemann sum, the first interval width is 4. Maybe I should just sketch that out. Okay, we have 55 degrees somewhere around here. We have an interval of 4. It goes up a little bit. There's my left-hand Riemann sum. 9 is going to be a little bit further along. It's going to go up again. There's another left-hand Riemann sum. 15, maybe somewhere around here. 15, and it goes up to 67 somewhere up here. Okay, and there's another left-hand Riemann sum, and then at 20 goes up to somewhere, something like that. Okay, so there's another left-hand Riemann sum. So if I want to find out this area, I'm going to take the interval width and the interval height. Okay, that's 55 high, 4 wide, so that's going to be 220. Okay, the interval width is 5 times 57.1 times 5. Okay, I'm getting 285.5 here. The next interval width is 6, and the interval height is 61.8. So that's 370.8. Okay, and the last interval has a width of 5 and a height of 71 degrees Fahrenheit, so 355. Okay, so it looks like this: 220 plus 285.5 plus 370.8 plus 355. Okay, add that all up and divide by 20. Okay, so I'm getting the average temperature of this interval is going to be 61.565. So I'm just going to round that to 57 degrees Fahrenheit. Okay, so that's the temperature times time divided by the interval time with 20 minutes, so the units are still consistent. Okay, so that is the average temperature. Does this estimate under or overestimate the real area? Since it is an increasing function, we're going to say that the area, so this is part B, this is an underestimate. Okay? The reason it's an underestimate because it is a strictly increasing function. Okay? So this is an increasing function. If the function was decreasing, we would be underestimating or overestimating the area. Is an increasing function. Okay. Okay, so for the last part here, D says for the interval, the W that models the water temperature is the first derivative. The first derivative function is W prime. They actually give you the function this time. Okay, and it asks you to find the water temperature at 25 seconds. Okay, so we know that T equals 0. The temperature, water temperature at 0 is 55 degrees. The water temperature at 0 is 55 degrees Fahrenheit. Okay. If I want to calculate the W function, W of T, okay, I need to use I can use the area underneath the W prime to get the displacement on the W function. So if I know that I start at 55 degrees and at T equals 0 to T equals T, okay, this function 0.4 square root x cosine 0.06 x. Okay, if I integrate that function, the area underneath this curve represents the displacement on the W prime. So this will, if I know where I'm starting, I can use that displacement here to calculate the actual value of at any point in time. Okay, in this case, it asks you T at 25. So T of 25 then looks like this. W of 25 is equal to 55 plus 0 to 25 seconds for the area underneath this curve. Okay, and then what we would have to do is this now becomes a calculator function. We would find the area underneath that curve using an integral function on the calculator. Okay, there's a few of them. I'm just going to go, let's see here. I'm just going to graph the function, and I'm going to find the area underneath that curve. So 0.4 square root x cosine of 0.06x. Okay, and then this is going to be times dx times dx. Okay, 0.06, I think I got that in there. Okay, so I want to graph this. I want to find the area from 0 to 25. Okay, so it's going to be working this out. And again, this integral has to be done on a calculator. We can't do this without a calculator. So I'm going to use the integral. And this is something that is unlikely going to be on the AP exam for 2020. Okay, we probably won't have access to the calculators then. So we're probably going to have to rely on the not having calculators do this. So you won't be getting questions like this. Okay, so I'm not getting an area here, but you guys can work out that area, and that becomes our position at 25 seconds.